Welcome back! In the last lesson, we learned that the fundamental theorem of algebra tells us the number of complex roots that any polynomial function will have. We also know that finding those specific roots is much easier when the function is in factored form. And while we know how to factor most quadratics, we don't have many tools that help us factor polynomials with a degree of 3 or higher. So today, you'll learn another tool to help you completely factor polynomial functions, synthetic division. Synthetic division will do what long division has helped us do in the past, but in a much faster way. In fact, compared to long division, you might even say that synthetic division goes at the speed of light. Ready? Let's get started. To help us get in the mindset of factoring polynomials, let's think about factoring in general. For example, if I needed to find all of the prime factors of 2,431, where would I start? Let's see. It's an odd number, so it's not divisible by 2 or any other even number. What about checking other factoring strategies that I know, like adding the digits to see if their sum is a multiple of 3 or 9? Let's try that. 2 plus 4 plus 3 plus 1 is 10, so I know that 3 and 9 aren't factors. Let's try dividing it by 7. That doesn't work. When I divided by 7, there was a remainder of 2, so 7 isn't a factor of 2,431. What should I try next? Oh, hey Mia! 17 is a factor? Well, that will certainly make things easier. Pause your video here and find all of the prime factors of 2,431. Now that you know that one of the factors is 17. How did you do? I divided by 17 and got 143 with a remainder of 0. That was a much easier number to work with, and it didn't take me too long to find 2 more prime factors, 11 and 13. So the prime factors of 2,431 are 17, 13, and 11. How does all of this relate to polynomials? In the last lesson, we saw how the fundamental theorem of algebra tells us the number of complex roots for any polynomial. We also saw that if we can go from this expanded polynomial to its factored form, we can easily find the function's specific roots, either real or imaginary, which also helps us learn a lot more about the function. But even though you know lots of factoring patterns and tools for factoring quadratics, you haven't really learned any good strategies yet for factoring anything with a degree of 3 or higher. So let's try to figure that out. Let's start with this cubic. F of x equals 2x cubed plus 9x squared plus 7x minus 6. What are its roots? Where do we start? Could one of its factors be 2x plus 3? Is it divisible by x minus 3? How can I tell? I could try using long division to begin dividing this by potential factors, but that would really be kind of a shot in the dark, and it might take a long time to narrow it down. So let's think back to 2,431. Once we knew that one of its factors was 17, it was much easier to find the remaining prime factors. So if I gave you a factor to start you off, what could you do with that information? For example, if I told you that one of the factors of f of x was x plus 2, what would you do? In Algebra 2, you learned how to use long division to divide polynomials by other polynomials. In fact, go ahead and try that in your notes. See if you remember how to use long division to divide f of x by x plus 2. Welcome back! Let's see how well you remembered the process. Check your work against mine. I set up the long division like this. After dividing, I got 2x squared plus 5x minus 3 with a remainder of 0. Long division is just one algorithm that we can use to divide polynomials. It serves its purpose, but it can be kind of tedious. For one thing, notice how many times I had to write down my variable. And because long division requires subtracting polynomial expressions several different times, it's also easy to make mistakes. The division algorithm you'll learn today, synthetic division, can save you a lot of time and effort. Synthetic division takes the key components of the long division process and boils them down to their most basic representation. So strap in! Are you ready? We are a go to learn how to use synthetic division. First of all, there are a few rules to follow. In order to use synthetic division, our divisor must be of the form x minus c. The x term must be linear, and for the type of synthetic division we are going to do, the coefficient of x must be 1. Second, your dividend must be in standard form. We'll go through the process first, and then I'll show you why it works. Here's what to do. Step 1 is to set up your problem by making a small box in the upper left of your workspace. Next to that, you'll list the coefficients of your dividend in the order of standard form: 2, 9, 7, and -6. Note that we do not need the variables here, just the coefficients. Under that row, leave a blank row for another row of numbers, and then draw a horizontal line, similar to if you were writing out an addition problem by hand. Step 2 is to determine what goes in the small box. This will be the value that, if plugged in for x, would make your divisor or denominator equal to 0. In other words, set x plus 2 equal to 0. What's x? Right, x is -2. Another way of saying this is simply to take the opposite of the constant value that you see in your denominator or divisor. In this case, the constant is +2, so we put its opposite in the box, or -2. Step 3 is simply to bring this first value straight down below your line. Our leading coefficient was a 2, so that's what gets brought down. This space directly below the 2 will remain blank, so feel free to draw this arrow and leave it here as a reminder. Now you're ready to get into the heart of the process. You'll repeat step 4 and step 5 until you're done. Step 4 is to multiply the value you just brought down below the line times whatever is in your box. So +2 times -2 is -4. Put that -4 in the next spot above the line, just below the 9. Step 5 is to add the two values and put the result below the line. 9 plus -4 is +5. Repeat step 4. Multiply 5 times -2 to get -10, which goes in the next spot below the 7. Step 5. Add to get -3. Step 4 again. Multiply -3 and -2 to get 6, which goes in the next spot. Repeat step 5. Add to get 0. Okay, we are essentially done, but this doesn't look like much, does it? The secret is that these values are the coefficients of our answer, our quotient. Since we just divided a cubic function by a linear function, I know that the degree of the result will be 2. So I just write these numbers as the coefficients, starting with an x squared term, 2x squared plus 5x minus the constant, 3. And because the final value was a 0, that tells us that we had no remainder. Therefore, this is the result after dividing 2x cubed plus 9x squared plus 7x minus 6 by its factor, x plus 2. Before we discuss why synthetic division works, let's take a moment to examine what we've done and how it helps us completely factor the polynomial. We started with the cubic function f of x. I gave you a known factor, x plus 2. We used synthetic division to divide f of x by x plus 2. And when we got a remainder of 0, it confirmed that x plus 2 is indeed a factor of f of x, because we divided and had no remainder. The result after dividing by the factor x plus 2 was 2x squared plus 5x minus 3, telling us that the entire function f of x can be factored into a linear factor and a quadratic factor. And that brings us to another question. Can this function factor even further? Pause your video here and try factoring the quadratic part of this polynomial. Okay, how did you do? I factored the quadratic into two more linear factors, 2x minus 1 and x plus 3. Now that all of our factors are linear, we know that f of x has been factored as much as possible, and this is its completely factored form. Now that we've seen how synthetic division can help us quickly divide a polynomial function by a linear factor, that brings us to the question of why? Why does synthetic division work? The process can seem somewhat mysterious the first time you see it, so let's take a close look at how it works and how it compares to long division. Here's the same function we've been working with, but now we can see long division and synthetic division side by side. Pause here a moment and use your PDF to make note of any commonalities and differences you notice. Here are some of the things I noticed. First, in synthetic division, I didn't need to use any variables. That means there's a lot less to write down and less repetition between steps. I only needed to add the variables all back in at the end. I also noticed that in long division, we subtract at each step, but in synthetic division, we add. How did we do the opposite operation but still get the same result? Do you see it? Right, because we used the opposite of positive 2. In a way, we're kind of pre-subtracting. In other words, because negative 2 is the opposite of positive 2, each value in this row of synthetic division ends up being the opposite of its counterpart in long division. Finally, you may be wondering why we were able to simply bring down this first 2 without having to do any figuring. Why did we do that? Because our divisor was in the form x minus c. That means that when we divided 2x cubed by x, the result, 2x squared, could be represented simply by bringing the 2 straight down, because 2 divided by 1 is 2. Let's do a quick example problem together before we wrap up for today. Okay, here's one for you to try. Use synthetic division to determine whether x minus 3 is a factor of x to the 4th plus 4x squared plus 5x minus 132. To answer this question, we can use synthetic division again. If we go through the division process and end with a remainder of 0, we'll know that x minus 3 is a factor because it divided evenly with no remainder. So let's get started together, and then you'll finish on your own in your PDF. Here are our steps. Step 1. Set up your small box. Be sure your dividend is in standard form, and then list out your coefficients. Let's see. 1, 4, 5, negative 132, and draw our line. Are we ready to begin? Or do you see anything here that we need to fix? I didn't mention it earlier, so it's understandable if you didn't catch it. But just like with polynomial long division, since our highest degree term is 4, we need to have every term or degree smaller than 4 represented. Which term is missing from this polynomial? Right, x cubed is missing. So we'll need to shift all of these over and put a placeholder of 0 between the 1 and the 4 to represent that missing x cubed term. Step 2. Fill in the box in the upper left. What will we put here? Remember, synthetic division only works if we're dividing by a factor of x minus c. What is c here? Right. This time, c is actually a positive 3, so be sure to put that number in your box. Now we're ready to begin. Finish the problem on your own and come back to check your work. All right, here's what I got. I brought the 1 straight down, multiplied by 3 to get 3. Remember to add. 0 plus 3 is 3. 3 times 3 is 9, and 9 plus 4 is 13. Multiply 13 times 3 to get 39, and then add that to 5 to get 44. Multiply 44 by 3 to get 132. Add that to negative 132, and there's our remainder. It's 0 again. That remainder of 0 tells us that, yes, x minus 3 is a factor of this quartic polynomial. And what is the resulting quotient? We started with a 4th degree polynomial, and we divided by a linear factor, so our first term will have a degree of 3. We have x cubed plus 3x squared plus 13x plus 44. Oh, hey, Mia! Let's recap what we did today. Oh, okay. See you later, I guess. Well, we can still take a look at the synthetic division big picture. First, we already knew that completely factoring a polynomial function will help us find the function's zeros, or x-intercepts. Today, we learned that synthetic division gives us a fast way to divide polynomials by their potential factors. If the remainder is 0, it confirms that the divisor was indeed a factor of the polynomial, and we can then continue factoring to get the polynomial into its completely factored form. Now, did you notice that for each example today, I gave you a starting factor to divide by? What would you have done if I hadn't given you those factors? Is there another way to narrow down our possibilities? Well, of course there is. And I hope that your curiosity is as boundless as the universe, because next time we'll find out exactly how to do that. Hey!